The Subcommittee on Space will now come to order. Without objection, the chair is authorized to declare recesses of the subcommittee at any time. Welcome to today's hearing titled Powering Exploration, an update on radioisotope production and lessons learned from Cassini. I now recognize myself for an opening statement. Exploration of our solar system continues to amaze and inspire us all. From rovers on the surface of our neighbor Mars to spacecraft visiting the distant reaches of Pluto and the recent completion of the extraordinary Cassini mission to Saturn, their discoveries are truly awe-inspiring. The exploration and science achieved by these missions is enabled by the production of plutonium-238, or Pu-238, and the radioisotope power systems, or RPS, that turn fuel into electricity for spacecraft. RPS are necessary for missions that go beyond Jupiter, where the sun's energy is simply not strong enough to power solar arrays, and for rovers that have unique mission requirements. Unfortunately, America's stockpile of Pu-238 is low. Despite efforts to reestablish production, this hearing allows us to review NASA and DOE's efforts to reconstitute Pu-238 production and better understand how critical it is to enabling scientific discovery and exploration. The Cassini mission was enabled by Pu-238 and its RPS system. Over the last 50 years, NASA has relied on RPS to power many of its missions into deep space. This was made possible by a ready supply of Pu-238 that was derived from weapons production. After the U.S. ended the production of nuclear weapons in the 1980s, Pu-238 was less plentiful, and so America has had to purchase Pu-238 from Russia. We no longer purchase Pu-238 from Russia and now find ourselves in a quandary. The existing stockpile of Pu-238 is all but gone. The infrastructure necessary to produce Pu-238 is being reconstituted, but as GAO will highlight, challenges remain. NASA funds the entire enterprise, but DOE owns and operates the facilities. Not all of the reactors involved in the production are currently active. Future missions to the outer planets will undoubtedly require Pu-238. Current assessments of the volume of Pu-238 that DOE can produce each year and NASA's assessment of its needs for future missions remain uncertain. For instance, when NASA assumes how much Pu-238 it needs, does it assume the fuel will be used in legacy multi-mission radioisotope thermoelectric generators, or MMRTGs, or in future advanced Stirling radioisotope generators, ASRGS, ASRGS are much more efficient and use less Pu-238, but the program was canceled a few years ago. Are NASA's estimated needs based on systems that are no longer being developed? NASA is also exploring plans to blend fuel to stretch its supply. Does this impact the quality of the supply and the missions that it can support? Since NASA is wholly dependent on DOE for isotope production, how will DOE's future management of its laboratories and reactors impact NASA missions? Is NASA planning missions based on low production rates, or are DOE's production rates determined by a lack of requirements from NASA? The recent completion of the Cassini mission offers us an opportunity to reflect on the amazing science and discoveries that were enabled by Pu-238. Stunning images and findings still stream in from the Curiosity rover on Mars, which is also enabled by Pu-238. NASA currently has roughly 35 kilograms of fuel left. NASA and DOE plan to produce 1.5 kilograms a year by 2025. A single MMRTG uses 4.8 kilograms of fuel. To put that into perspective, Cassini used 33 kilograms in one mission. I look forward to your insightful testimony about the future of exploration and how we can ensure that we continue to push the envelope of discovery. Thank you to our witnesses and their staff. You were able to accommodate a compressed schedule to appear today. Your service to the committee and nation is greatly appreciated. And now I'd like to recognize the ranking member, the gentleman from California, Mr. Barra, for an opening statement.
Thank you, Mr. Chairman, and thank you for calling this hearing, and good morning and welcome to the distinguished panel. You know, part of the reason why I like these hearings is, you know, I'm a simple doctor, a physician, and I get to interact and listen to the scientists, and I would not have thought I'd be talking about plutonium-238. But in truth, this is an exciting time for space. It's an exciting time for space exploration. Thinking about how we're going further and further into space. The dramatic discoveries of Cassini. Looking at the moon and Enceladus, and perhaps harboring the ingredients of life. And the more we want to go further and further, we're starting to recapture the imagination of a public with these discoveries. But that then comes in to, as we go further, what are our energy sources going to be in terms of communicating with us? And I think that's why this is such an important hearing. Cassini was operated, the radio power systems were operated by plutonium-238, and we stopped producing that a while ago. I think the chairman's highlighted the challenges there and the big questions that we have that we look forward to hearing from all of you about. A couple questions that I have is the DOE on track to produce NASA's supply requirements of PU-238 in the anticipated time frame? A second question that I would hope that you're able to address is, what impact would PU-238 shortfalls have on NASA's planetary science plans and future portfolio? A third question would be, are there mitigating actions available to address the constraints of the PU-238 supply? And a fourth question that I would hope that you're able to address is, have NASA and the science community already been making science-limiting decisions based on the PU-238 supply constraints? So, Mr. Chairman, with that, I look forward to hearing what the witnesses have to say, and I yield back.
Absolutely, thank you. Good statement. And I'm a simple dentist, and you're a simple physician, right? Okay. And let's see, I'd like to recognize
outer regions of the solar system and on the surface of Mars. Today is the 60th anniversary of Sputnik launch that ignited the space race with the former Soviet Union. In the intervening decades, federal investment in NASA's Planetary Science program has enabled NASA to send spacecraft to the farthest reaches of our solar system and beyond. Thanks to Curiosity, which landed on Mars in 2012, we know that ancient Mars could have had chemistry necessary to support life. Curiosity also has detected methane in the Martian atmosphere, a possible sign of microbic activity and evidence of ancient water flows. The recently completed Cassini mission spent more than a decade observing storms in Saturn's cloud tops, probing the planet's hidden interior, observing Saturn's rings with unprecedented detail, and flying through the geysers of Saturn's moon. In Enceladus, the New Horizons mission became the first mission to perform flyby of Pluto and subsequently discovered that Pluto is still geologically active, has an extensive blue atmosphere, and is home to the largest known glacier in the solar system. What do all these missions have in common? All of these missions and the groundbreaking science they enable are driven by the radioisotope power. NASA is developing future missions that require radioisotope power as well, including Mars 2020 rover that is currently in development. In 2009 and 11, National Academy's report sounded alarm about the supply of materials needed for radioisotope power and underscored the need for immediate action to restart domestic production of PU-238 and the non-weapon grade isotope that makes radioisotope power systems work. Mr. Chairman, it is vital that NASA is equipped with the power resources that it needs to continue to lead in the scientific exploration of the solar system. NASA's partnership with the Department of Energy has been and will continue to be essential in enabling the use of radioisotope power systems. I look forward to a fruitful discussion on what NASA and DOE are doing to cost-effectively ensure a significant supply of materials needed for radioisotope power systems to meet NASA's needs in the future. I thank you, and I yield back.
Now I'd like to introduce our witnesses. Mr. David Schurr. Is it Schurr or Schurr? Schurr. Our first witness today is Mr. David Schurr, Deputy Director of the Planetary Science Division at NASA. He received a Bachelor's of Science degree in Aerospace Engineering from the University of Notre Dame and a Master's of Science degree in Process Control from the University of Houston. He also received a Master's of Business Administration degree from the University of Houston. Thank you. Good to have you today. Ms. Tracey Bishop, our second witness today, Deputy Assistant Secretary for Nuclear Infrastructure Programs in the Office of Nuclear Energy at the Department of Energy. She holds a Bachelor's of Nuclear Engineering degree from the Georgia Institute of Technology and a Master's of Business Administration degree from the University of Maryland. Welcome. Dr. Ralph L. McNutt, Jr., our third witness today. He's Chief Scientist for Space Science in the Science Exploration Sector at the Johns Hopkins University Applied Physics Laboratory. He received his Bachelor's of Science in Physics at Texas A&M University and his PhD in Physics at MIT. Welcome to today's hearing. And Ms. Shelby Oakley, our fourth witness today, Director of Acquisition and Sourcing Management at the GAO, Government Accountability Office. She earned her Bachelor of Arts degree in both psychology and sociology from Washington and Jefferson College, as well as a master's degree in public administration from the University of Pittsburgh's Graduate School of Public and International Affairs. And we welcome you as well. I'd like to now recognize Mr. Schurr for 5 minutes to present his testimony.
Chairman Babin, Ranking Member Barra, and members of the subcommittee, thank you for the opportunity to discuss how NASA's radioisotope power systems program enables our planetary exploration portfolio. My office pursues NASA's goal to ascertain the content, origin, and evolution of the solar system and the potential for life elsewhere. For many destinations in the solar system, solar power is not effective for powering our spacecraft, and we rely on the use of radioisotope power. NASA, in partnership with the Department of Energy, has deployed radioisotope power on 22 of our space missions since 1969. Use of radioisotope power has enabled many first-time missions, including the first visits to Jupiter and Saturn with Pioneer 10 and 11, the first landings on Mars with Viking 1 and 2, the first visits to Uranus and Neptune during the grand tours of Voyager 1 and 2, the first rovers on Mars with Pathfinder, Spirit, Opportunity, and Curiosity, the first mission to orbit Jupiter with Galileo, the first mission to orbit Saturn with the just completed Cassini, and the first visit to Pluto with New Horizons. These missions would not have been possible without using the heat generated by the natural radioactive decay of plutonium-238 to generate electrical power. To ensure that NASA is capable of conducting these missions, NASA and DOE work together to sustain and improve the technology to convert heat into electrical power and the processes for producing plutonium-238 and preparing it for flight. NASA funds the implementation of the DOE-led plutonium-238 production and the associated infrastructure needed to fuel and test radioisotope power systems to fulfill NASA mission requirements. Progress in reestablishing a plutonium-238 production capability has been good, with initial batches already produced and shipped to Los Alamos National Laboratory for mixing with existing inventory and pressing into fuel clads for NASA's upcoming Mars 2020 mission. NASA's mission requirements for plutonium-238 are driven by the mission priorities established in the Planetary Science Decadal Survey, as well as other potential NASA missions. At this time, the Mars 2020 mission represents the only firm NASA requirement for radioisotope power, needing one multi-mission radioisotope thermal generator requiring 4.8 kilograms of plutonium dioxide. NASA has also offered mission proposers the option to use radioisotope power for the current New Frontiers 4 competition for possible launch in 2025, and has forecast a potential to offer radioisotope power for New Frontiers 5 or a potential flagship mission launching around 2030. With the current allocation to civil space of approximately 35 kilograms of plutonium, and with new production ramping up to 1.5 kilograms of plutonium dioxide per year, DOE will have sufficient material for fabrication into heat sources for expected planetary science missions through 2030. In addition, NASA and DOE have begun exploring options to increase production rates if needed to support any increased future demand. NASA also conducts basic and applied energy conversion research to advance state-of-the-art performance in heat to electrical energy conversion. Both static and dynamic energy conversion projects are underway. All missions to date have used a static conversion system based upon thermocouples. Dynamic conversion can achieve higher efficiency, but the moving parts introduce challenges that must be addressed before committing to flight development. The goal of these investments is to provide higher conversion efficiency and improve performance for future missions. Increased efficiency would benefit the program by enabling more capable missions or extending the effective use of the plutonium-238 supply. With the 2016 New Horizons flyby of Pluto, humankind has completed its initial survey of our solar system. Through the use of radioisotope power, the U.S. remains the first and only nation to reach every major body from Mercury to Pluto with a space probe. With your continued support, we will use these capabilities to continue to explore the solar system through more capable orbiters, landers, and sample return missions in the years to come. I look forward to responding to any questions you may have.
Thank you, Mr. Schurr. Appreciate that. I now recognize Ms. Bishop for 5 minutes to present her testimony.
Chairman Babin, Ranking Member Bera, and members of the subcommittee, thank you for the opportunity today to discuss the Department of Energy's efforts to ensure radioisotope power systems are available for NASA use. The department is committed to its partnership with NASA to provide radioisotope power systems for space exploration. This successful partnership has extended over 50 years and 22 missions. Radioisotope power systems have a proven track record with no failures and long power lifetimes, making them a continued viable technology option for NASA missions. In October 2016, the department and NASA renewed a memorandum of understanding to work together on future development and deployment of radioisotope power systems. This arrangement updated agency responsibilities to reflect funding authority changes and to provide more emphasis on aligning and integrating work to ensure and enable future space exploration missions. In the same month, the Office of Nuclear Energy realigned responsibilities to the Office of Nuclear Infrastructure Programs, elevating interface with NASA to the Deputy Assistant Secretary level. Upon approval of the new Memorandum of Understanding, the agencies initiated discussions to assess current activities and to determine options to support for NASA mission goals. In early 2017, the Department and NASA agreed to transition delivery of radioisotope power systems from a mission-driven approach to constant rate production strategy. Constant rate production establishes clear deliverables as defined by annual average production rates for plutonium-238 and fuel clads, allowing the department to level load work, ensuring that the capability is fully exercised, technical proficiency of the workforce is maintained, and opportunities to maintain and refurbish equipment in a systematic approach are available to support NASA mission requirements. Measurable progress has been made to realign activities to directly address identified risk to achieving plutonium production rates. The department completed its first campaign of new domestic plutonium-238 in 2015, and the new material met NASA mission specification requirements. The department and NASA agreed to continue efforts to reconstitute the plutonium supply chain by utilizing this material as part of the Mars 2020 mission. I'm pleased to report that as of August 2017, the department successfully fabricated 2 fueled clads utilizing new plutonium for the Mars 2020 mission. A second campaign of new plutonium is scheduled to complete this fall, taking into account lessons learned from the first campaign. The department is actively working to address and mitigate risk to establishing domestic plutonium-238 production. Additional funding was made available as part of the fiscal year 2017 omnibus, and the department is utilizing those funds to further reduce risk and accelerate schedule. For example, the department is accelerating work to expand the capability to ship larger quantities of plutonium-238 heat source oxide between its sites. The department is also accelerating research and testing on production target design with a goal of recommending a standard target design for both the Advanced Test Reactor at Idaho National Laboratory and the High Flux Isotope Reactor at Oak Ridge National Laboratory by 2019. The department has an existing inventory of plutonium-238 that is able to meet NASA's current demands through a no-shield mission in 2025, plus additional plutonium that is currently out of specification. The department recognizes there is a need to develop long-range projections of plutonium to support space exploration planning activities beyond 2025 and is initiating several activities to begin this work. The department accelerated an experimental campaign to verify an approach for irradiation in underutilized positions in the Advanced Test Reactor that would yield sufficient quantities of very high assay plutonium, which can be blended with the existing larger quantities of out-of-specification inventory to support overall heat source production rates while minimizing impact to existing irradiation customers. The department is also assessing options to support redesign of the high-flux isotope reactor's beryllium reflector to optimize it for plutonium-238 production, with the potential to increase total yield and assay so that it could also be blended with larger amounts of out-of-specification plutonium. The department remains committed to partnering with NASA to ensure continued availability of radioisotope power systems for space exploration missions. Thank you for the opportunity to share the department's progress, and I look forward to addressing any questions you may have in this area.
Thank you, Ms. Bishop. I now recognize Dr. McNutt for 5 minutes to present his testimony.
Chairman Babin, Ranking Member Barra, and members of the subcommittee, thank you for providing this opportunity for me to discuss some of the things that we've been able to do with these radioisotope power supplies over the years and some of the challenges that have been going on in order to be able to actually make a lot of these discoveries. Of course, it's already been remarked that 60 years ago today, Sputnik was launched. It was powered by a battery. It was not until the 4th mission, Vanguard 1, that was launched by the United States, that there were actually solar cells that were used. Solar cells were a problematic technology at the time. We've come an incredibly long way since then, but at the time there were issues about whether that they would actually be able to be useful. And so the development of radioisotope power supplies was begun early. The first use was on the Transit 4A satellite, launched in 1961 as part of the Navy's communication system. And since then, the United States has poured a great deal of effort and money into maturing the radioisotope power system supplies that we've been using until today. And of course, things like the Pioneer 10 and 11 probes, the first ones beyond the asteroid belt, the Viking 1 and 2 landers, the first landers on Mars, and now even the venerable Voyager 1 and Voyager 2 space probes, which have celebrated more than 40 years in space and are still broadcasting from beyond the edge of the solar system new data about our surroundings. None of these would have been available if it had not been for these power supplies. It's also been remarked about the Cassini mission, of course, and I think I've got a graphic, and that is indeed up. Of course, trying to describe everything that's been done with Cassini over the last 13 years in orbit is something that would take considerably more than 5 minutes. But certainly our discoveries at Titan, our discoveries about Saturn, its rings, the magnetosphere, how similar and different the magnetic fields of Saturn and the Earth are, as well as looking at Enceladus, of course, and the plumes, which have already been talked about as perhaps places where that there might actually be life, are all things that would not have been possible without those power supplies on board the spacecraft. And if we could go to the next slide, please. And of course, also with New Horizons, on the left-hand side is the best Hubble image of Pluto. and in the middle is what we were able to get with New Horizons, nine and a half years of flight. And the final image is actually looking back toward the sun with the New Horizons spacecraft, and you can see the haze around the edge. This is a movie. This is actually put together from actual data that was gathered by the New Horizons spacecraft, showing you what the glaciers look like, made out of nitrogen ice, water mountains, very young features, all geologically active, as has also been already remarked about. Basically an incredible world out at the edge of the solar system. And again, if it had not been for having these radioisotope power supplies, none of this would have been possible. Of course, one of the things has also been noted is that at the time of the Academy report in 2009, it looked like we were into a going out of business sale with being able to actually have plutonium supplies to be able to do these kinds of missions. The good news is that we were able to actually recover from that, as already has been noted by my other colleagues here at the table. We seem to have turned the corner on that. At the same time, this is a difficult business, and the converters that NASA has been investing in, DOE has been investing in, these have been technically hard problems. It's been elusive in trying to raise the types of efficiencies that one would like. And indeed, the type of radioisotope power systems that are on board Cassini and on board New Horizons right now are technologies that right now we cannot reduplicate. We cannot rebuild those supplies. It's been a difficult time trying to come up with a sort of a power supply where that one supply will fit all. And that has particularly remained elusive. Of course, it's limited by the amount of funds that are out there, but nonetheless, there are other steps that perhaps could be taken in order to enable us to keep moving forward. Certainly within the scientific community, great deal of interest in the decadal surveys with future missions that cannot be done any other way. And I look forward to being able to answer any questions that you might have about some of those missions or any of the other aspects of these supplies and what they've been able to do for us. Thank you.
Thank you, Dr. McNutt. I recognize Mrs. Oakley for 5 minutes to present her testimony.
Good morning, Chairman Babin, Ranking Members Johnson and Barra, and members of the subcommittee. I am pleased to be here today as the simple analyst on the panel to discuss the current status of radioisotope production to enable future exploration. As you know, radioisotope power systems, or RPS, have enabled many of our most ambitious exploration missions, such as Curiosity and, of course, Cassini. DOE has been providing RPS to NASA for over 5 decades. However, our continued capability to produce RPS is dependent on a ready supply of Pu-238, the highly radioactive isotope used to power RPS. From the late 80s until recently, we haven't produced any Pu-238 in the U.S., and our national stockpile that can be used in RPS is about 17.5 kilograms, about half of what was used in Cassini. With one mission expected to use RPS Mars 2020, and one that may potentially use RPS New Frontiers number 4, the Pu-238 stockpile could be exhausted as early as 2025. In 2011, NASA began funding DOE's efforts to develop new Pu-238 through its supply project. Timeframes and costs for the supply project have shifted and increased since 2011, and it will be 2025 at the earliest until DOE expects it can reach its full production goal of 1.5 kilograms per year. Until it does, questions will remain about NASA's ability to plan for and execute scientific missions that rely on RPS as an enabling technology. With this information as a backdrop, today I will discuss our recent work looking at how NASA selects RPS-powered missions, what factors affect such demand, and the progress and challenges DOE faces in meeting NASA's demand. Regarding mission selection, NASA officials acknowledged that the availability of Pu-238 has been a limiting factor for selecting missions that require RPS, particularly prior to the establishment of the supply project in 2011. For example, NASA did not offer RPS up for New Frontiers number 3. Based on DOE's progress, NASA has now indicated that it is currently not a limiting factor, but one of several factors it considers in mission selection. These other factors include scientific priorities and objectives, costs and timeframes, and policy direction. NASA officials indicate they prioritize mission selection based on the decadal survey, which represents the highest priorities of the scientific community and includes many missions that may require RPS. According to NASA, it can only do 2 to 3 RPS missions using RPS per decade. Traditionally, RPS have been used on what NASA refers to as flagship missions. Flagships typically cost $2 billion or more, and as our previous work has shown, frequently experience cost overruns and schedule delays. As a result, the projected rate of these kinds of missions, due to their high cost, has allowed the demand for RPS to be met, at least in the near term. For other less expensive missions, the cost and time it takes to produce RPS makes their use a little more challenging. Finally, it is important to note that consistent with national space policy, NASA uses RPS for missions when it enables or significantly enhances the mission, or when alternative power sources would compromise mission objectives. Sometimes it's evident that RPS is the only option, but other times more work is needed to determine if there's an alternative source available, such as solar, as was the case with the Europa Clipper mission. Regarding supply, DOE is making progress toward producing new plutonium-238. So far, DOE has produced approximately 100 grams of new Pu-238 and has initiated efforts to ensure it has sufficient equipment and facilities to meet NASA's demand. However, DOE faces challenges in hiring and training the necessary workforce, perfecting and scaling up chemical processing, and ensuring the availability of reactors that must be addressed or its ability to meet NASA's needs could be jeopardized. Addressing these challenges will take careful planning and coordination. However, we found that DOE and NASA could do more in this regard. For example, we found that DOE doesn't have a long-term plan in place that identifies interim steps and milestones to allow it to show progress in meeting production goals, or how risks are being mitigated. We also found that DOE's prior approach to managing the work doesn't allow it to adequately communicate systematic risks to NASA and their potential on programmatic goals. Having such information would allow DOE and NASA make adjustments to the program if necessary and better plan for future missions. We made recommendations to DOE aimed at better planning and communicating risks. DOE concurred and has identified actions it's taking. Chairman Babin, Ranking Member Baer, and members of the subcommittee, this concludes my remarks. I'm happy to answer any questions that you have.
Thank you, Ms. Oakley. I thank the witness for your testimony, and all of the witnesses. The chair recognizes himself for 5 minutes, and I'm going to ask a question of Mr. Schurr, but I would like to answer it as briefly as you possibly can, but cogently, of course. And then I want to try to get in as much as I possibly can from some of the rest of you folks. Mr. Schurr, your testimony states that NASA has approximately 35 kilograms of plutonium dioxide. You also stated that NASA expects DOE to begin initial operations of Pu-238 production in 2019 with the goal of producing 400 grams of plutonium dioxide annually and ramping up to 1.5 kilograms per year by 2025. Finally, you stated that this production rate would satisfy expected NASA planetary science mission requirements through 2030. Of the 35 kilograms of Pu-238 allocated to NASA, how much of that is viable for use in an RPS system for space flight?
Currently, about 17 kilograms of the 35 meets the specifications for our use for space flight. So what's valuable to us is as we start ramping up the initial production of the new plutonium, which will be at a higher assay, a hotter material, we'll able to blend that with the remaining 18 kilograms or so that is not to specification. So in the short term, the missions that we've got with Mars 2020 and a potential mission in 2025, we have all the materials we need. For a mission in the 2030 timeframe, we will rely on the new production to blend with the rest of the material that's in inventory that's not a specification.
Okay, thank you. Does your assessment that planned production will meet NASA requirements assume the use of multi-mission radioisotope thermoelectric generator technology or advanced Stirling radioisotope generators technology?
At the moment, we're assuming the MMRTG is the baseline, since the ASRG does not exist and it's not in our inventory. But we are looking at alternatives and improvements to the basic MMRTG technology. But right now, we assume that's our baseline.
Okay, thank you. How much PU 238 does an MMRTG require versus an ASRG?
The MMRTG uses 4.8 kilograms of plutonium dioxide, and the ASRG is 1/4 as much for the same amount of power.
Okay, just wondering if we need more PU 238 than we're thinking. Does your assessment that planned production will meet NASA requirements also factor in the potential needs of the human exploration community?
At this point, we're not making any assumptions about needs for human exploration, Mars or elsewhere. If for a human spaceflight, if we determine that there's a value for PU 238 in their activities, it would likely require an increase in production. And that's part of what we're working with DOE. What are our options to do a higher rate of production if needed?
Okay, thank you. And lastly, if some portion of NASA's existing stockpile of 35 kilograms of PU 238 is not currently flight worthy, and NASA's assessed need for future missions is based on systems that are more efficient that we currently produce, does NASA only need 1.5 kilograms per year for PU 238 from DOE to meet its existing demands, or could it use more? And also, what are we losing by not employing RPS for human missions?
There's a lot in there. We certainly could do more missions at a higher rate, but the number of missions that we can go do in a decade, for instance, is also constrained by how much budget we have for the missions of that scale, as well as the other activities that we're doing in planetary science. So what we've been trying to do is get a balance right between what we think is a reasonable forecast and making sure that we've got the capability and the plutonium available to meet that forecast.
Okay, thank you. Ms. Tracey, based on the National Nuclear Security Administration's Global Threat Reduction Initiative, DOE committed in 2012 to convert all research reactors to a low enrichment fuel for non-proliferation concerns. The high-flux isotope reactor at Oak Ridge National Laboratory is approaching 60 years of age and uses highly enriched fuel. What is the certainty of continued use and availability of HIFR, HIFR?
Thank you for the question. The mission for HIFR is continuing on within the department. My organization, along with other elements in the department, continue to work with the National Nuclear Security Administration regarding efforts to convert the research reactors from highly enriched uranium to low enriched uranium fuel. At this time, I do not have any indications regarding impact to future missions or the ability to impact NASA's goal to produce plutonium-238.
Okay, thank you. I had a lot more, but my time has expired, so we will go to the gentleman from California, Mr. Barrow.
Thank you, Mr. Chairman. We currently have 35 kilograms of PU 238. That's our current stockpile, Mr. Schurr?
That's correct.
And there was a time where we were purchasing PU 238 from Russia, but Russia has now indicated they don't have the supplies, or is it that they don't want to sell us supplies, Mr. Schurr?
I have to admit, all those activities predated me, and they've been closed down for a while.
Okay.
I don't know, Tracy, if you've got anything to add to that.
Those discussions also predated my
Okay.
involvement.
So regardless, they may have supplies, but they don't want to sell them to us, or they no longer have supplies.
We currently have no negotiations or discussions going on with the Russians regarding PU 238.
And it's reasonable to assume that there are no other countries currently capable of producing PU 238 that we know about.
That's correct.
In thinking about what our needs are by 2025, we've got the 35 kilograms. What would you say our needs are between now and 2025, Mr. Schurr?
The most that we can envision that we would use between now and 2025 is about the 17 kilograms that's within specification. Through 2030, we could possibly use that full 35, but we would have to bring the rest of it up within specification. And that's where the new production is required.
Okay. And we would, I think the chairman asked questions if there are missions we'd consider without the RPS, but it wouldn't make sense, I think, if we're going to deeper space, not to have that ability to collect and communicate.
That's correct. We have now demonstrated we could do missions as far away from the sun as Jupiter. The Juno mission's currently there. The Europa Clipper mission will be going there. I've seen proposals that can go as far as Saturn for fairly limited missions. But beyond that, solar power is not really going to be useful, and we need an alternative source, such as RPS.
Okay, and we'd certainly want to have some certainty that we're not, sending a mission pretty far out and not certain whether solar power.
Correct, and we have high-priority missions that are out to Uranus and Neptune that are part of our decadal survey that we want to maintain the ability to service.
Great. Is there any science going into other alternative fuel sources, or is it PU-238 that is the source that we'd have to be using? And is all the science on improving conversion, blending it, making it a bit more efficient?
There's been a lot of work historically looking at what are the best isotopes to use for power conversion. PU-238 tends to come up on top for many reasons as one of the best, and the infrastructure is in place today. So as far as isotopes go, we wouldn't really look at a different radioisotope. There's a possibility that fission might be developed in the future, and we'll look at what missions a fission system could possibly support, but likely it's not everything we're trying to do with planetary exploration. We're also looking at what are the different power conversion technologies? How can we advance thermocouples to be more efficient than what we've got right now? We have a technology project underway today to improve thermocouple efficiency. And we're also continuing to explore dynamic power, which is the basis for the ASRG, to see if we can come up with a more efficient system there.
Dr. McNutt, would you have some thoughts on this as well?
Well, I think that, David's put the case fairly well. Certainly the idea of being able to have a dynamic converter is something that we've been talking about for a long, long time. And the problem is these have always fallen short. There are technical reasons. There's a lot of concern about whether that if one had a dynamic power system, is that something that you really want to rely upon, having the moving parts? And there's a great deal of debate back and forth in the community about that. So as I mentioned, certainly the GPHS RTGs, these are the ones that were used on Cassini, Galileo, Ulysses, New Horizons. Those were sort of the top level power supplies we were able to put together, which will work in a hard vacuum. They won't work on the surface of Mars for technical reasons. And, but again, they're the sort of thing that we've sort of backed away from, partially because we were looking for the one-size-fits-all kind of a unit. With respect to other isotopes, David's actually absolutely right. That sort of thing has been examined over and over and over again, a great deal in the 1950s and 1960s especially, and for all sorts of technical reasons, plutonium-238 in the dioxide form is the only thing that really makes any sense.
So if we're projecting into the future, past 2025 and further, we know more of the international community is getting involved and thinking about space exploration. As we go into deeper and deeper space, it is my perspective that we will be doing that in partnership with the international community. If we do more human space exploration, whether it's human exploration of Mars, et cetera, we'll also need reliable energy sources, et cetera. It's not easy to produce PU-238, obviously. We potentially become the only supplier of PU-238 with missions that are beyond what we're just thinking about within NASA and our own scope. And I'm not sure we want other countries, producing PU-238 or encouraging that. That wouldn't necessarily be a good thing. So one thing that I would urge us to also think about is, as we're ramping up production beyond 2025, is how do we meet the international community's needs potentially as well? Am I thinking about this correctly? Because again, I don't think we want other countries exploring PU-238 production.
Well, certainly one of the things that's happened in the United States is that if you look at inflation-adjusted dollars, there's been about about $6 billion that went into developing these supplies. And of course, we've already had that kind of an international partnership because the Ulysses spacecraft was actually built by the European Space Agency, but we provided the GPHS RTG that actually enabled that mission. And there have been other discussions with other space agencies, notably with ESA, about trying to duplicate that or replicate that, having similar things go ahead in the future. But the bottom line is as David was saying, is that once that you get beyond Jupiter, and especially with some of the things you'd still like to do at Jupiter, you just simply cannot do them without this, and the United States is the premier developer of the technology, the owner of the technology, the owner of all of the intellectual property. We're the ones that know how to do this. It's been a very hard-fought battle getting to that point, and it's something that I think most members of the Science Committee would hope that we don't lose.
I would hope so as well. Thank you for.
Yes, sir. Gentleman's time has expired. Now let's go to the gentleman from California, Mr. Knight.
Thank you, Mr. Chair. I'm going to go in a little bit different direction, probably to Mr. Schurr or Dr. McNutt. Are ASRGs, are they already assumed in deep space exploration? Is that NASA is already taking those into effect or into account?
The ASRG project itself, the flight project, was canceled back in 2013. So right now, we don't build it into any of our forecasts for future needs as a system that would be available to us. We're still investing in the technology to see if we can develop a technology from that, but we don't build it into any of our forecasts.
Okay, so if we go down the road of going to Mars in the next 16 or 17 years, as the bumper sticker says, if my good friend from Colorado would be here, Ed Perlmutter, he would have his bumper sticker out there. If we assume we're going to make it there in the next 16 years, a lot of these efforts have got to be, or a lot of these problems have got to be fixed. One of them is the propulsion. Obviously, the number one is the radiation to make sure that our astronauts get there and they get back safely. That's always the number one mission. If we are going to get there a little faster, to make sure that the radiation impact is lessened because of less travel time. Is that going to be a part of a new propulsion system, or is that going to be a propulsion system that might be nuclear powered?
I don't believe there's a relationship between the Stirling power conversion and the NTP, the nuclear thermal propulsion. So you see Stirling gets involved when you want to convert the heat that comes off
Right.
the reactor into electricity.
Right. Okay. But again, if I just follow that question or that line of thinking, we're going to need that kind of propulsion system to get us there quicker. Is that correct?
I actually have to admit that's not my field of expertise. So in the planetary science, our focus is on power conversion, and I know we have folks in our space technology organization that are working on NTP.
Okay, and now I'm going to go back to what the chairman said about the 35 kilograms. If we have enough to make sure that we're going through 2025 or 2030, and the conversion of this 35 kilograms is proper, or we have enough, wouldn't the ASRGs be a part of that at some point to make sure that we have the burn rate or the conversion rate, or some other technology? It could be something else.
If we're able to develop a dynamic technology that is 4 times more efficient, we'd be able to stretch the supply to conduct 4 times more missions or larger missions. So it is something we are investing in to see if we can make it work. It is technology that would also be applicable to any human-based usage with a fission-based system if one were developed. So the technology has multiple uses, any heat source conversion to electricity. So it is an area that we're going to continue to invest in. Whether it makes sense for planetary missions or not, we have to solve some of the issues that Dr. McNutt was referring to. A dynamic power system with moving parts that can't be maintained for 20 years, you have to make sure there's enough reliability in the system. But those are the things that we're investigating.
Okay, very good. I yield back the balance of my time.
Okay, nobody down there. Nobody down there. I'm gonna call him Posey. Yeah. Okay. Gentleman from Florida, Mr. Posey.
Thank you very much, Mr. Chairman. Questions for each member of the panel. Are you aware of any destruction of the United States supply of RU-238 in the past?
I'm going to defer to my colleague from Department of Energy.
Sir, I'm not aware of any destruction of PU-238.
Anyone else hear any rumors of it at all? Okay. In 2004, we had Dr. Jim Green, director of NASA Planetary Science Division here, and he indicated there was absolutely no problem whatsoever with future supplies of RU-238. And Mr. Schurr, you've kind of indicated the same thing, but the Inspector General leads me to believe there might be a problem with it. What's the deal here?
I think what we were trying to convey in our report was more that there was a limiting factor. The PU-238 was a limiting factor in the early part of this decade. That, coupled with a lot of really significant overruns on planetary science missions, I think limited even the number of missions that planetary science could undertake, let alone the ones that would need PU-238. Right now, based on the development of new PU-238, blended with the old, the needs are met in the near term. Our report tries to convey the fact that if this new supply of PU-238 isn't established and the goals aren't met by DOE, then it could become a limiting factor again in the future.
Well, I would think, it's common sense, that if we know we're going to need more in the future, we would have some plan, some coordination between NASA and DOE to furnish a supply or produce a supply. And the information that I seem to be getting is there really is no firm coordination or agreements or efforts to do that at this point.
I think I'd say it a little bit differently. In 2012, we kicked off with the Department of Energy a restart of the plutonium production project. So we've been investing since 2012.
Okay, now bring me up to date on that. Where's that progressed to? At what point are you in then?
We've now produced up to 200 grams.
We produced 100 grams
100
of
grams.
new material. We have a second campaign underway that should end this fall. That's going to produce approximately the same amount of material. And we are continuing our efforts to reestablish our infrastructure and our pipeline to produce the rates that NASA requires to support their mission activities.
And does NASA's request take into consideration maybe a loss of a launch and might need to replace that?
Not specifically, but since the only firm mission that's on our books right now is the Mars 2020 mission, we clearly would have the ability to replace one MMRTG's worth of fuel if we were asked to do so.
Well, I've heard the date, the 35 that we have now potentially being utilized by 2025, is that correct?
About half of that could be used by 2025. The other half needs the blending of the new material and would cover our needs through at least 2030.
And beyond 2030?
We would need the new production that's coming online, which should be to full operational capability by 2025. And at that point, we're already starting the discussions about whether we want to raise the rate if we need it for future forecasts.
Okay. Thank you, Mr. Chairman.
Yes, sir, thank you. I'd like to call on the gentleman from Florida, Mr. Dunn.
Thank you very much, Mr. Chairman. Let me start, if I may, with Mr. Schurr and Ms. Bishop. How does NASA communicate their needs for regarding the RPS for PU-238? How do you communicate with each other, and do you feel like you've got enough lead time on that?
I mean, we have many regular processes. We have a monthly management review where we sit down and look at all of the progress in their activities, as well as talk about any changes in our activities. Then we have a formal process as part of the annual budget cycle where
So you feel like you're interconnecting well, both of you?
I would
Is that
say
fair?
so.
Yes, I would agree.
Okay. For Ms. Oakley, does DOE have an assessment of the total cost requirements to upgrade the facilities to undertake the polonium-238 production, and who pays for that?
Well, the bottom line, sorry. The bottom line is that NASA will bear most of the cost to upgrade the facilities and prepare all of the.
That's not spread over any of the other users of 238?
No,
PU-238.
not that I understand. No, and NASA's the primary user right now, and NASA is responsible for reestablishing the capability for the United States. So they've been providing the funding to DOE through the supply project since 2011. And so I think that if you want to talk about cost, this is one of the criticisms in our report that we had, is that prior to recent changes that Ms. Bishop discussed, the supply project was being managed in a very segmented, short-term approach because of uncertainties about funding that would be available in any given year. So it was really difficult to project how much this was going to cost overall. So in the beginning, we were being told it was about $85 to $125 million to reconstitute this effort. Now it's looking like it's going to take a little bit longer and be more upwards of about $235. That being said, because of the way the project was being managed before, we don't know exactly if this is a realistic accounting of risks that are involved in reestablishing that process.
Do I misunderstand? Does DOE, you're producing this PU-238 also, or 239, for weapons?
That's not my area of
I'm not
purview.
sure, but DOE is the one doing it, right?
The Department of Energy is producing plutonium-238 to support
So-
NASA mission requirements.
So are those two parts of DOE talking to each other? I mean, we're making this stuff, so maybe they can get some, NASA doesn't have to start all over?
We coordinate very closely with NASA regarding mission needs as well as their requirements for plutonium. Also, with our arrangement with NASA, the department employs full cost recovery. So we go forth and look at the infrastructure that NASA needs. If it is shared infrastructure, for example, at Los Alamos National Laboratory, where the infrastructure is shared with other national security customers, there is a cost-sharing arrangement. So
Have you now reprocessed all of the Russian plutonium we got from the warheads at the end of the Cold War there?
no, the Russian material is still part of the stockpile that we currently have available.
That 17.5 or 35, whatever?
Kilograms, yes.
Okay, so that's it, that's the last of it.
Yes.
That's it, okay. Just turn for a moment here. I think this is a Mr. Schurr question. Please compare the relative development levels, which is ready first, of the RTG, the ASRG, and the kilopower fission system. Which one can we expect to be online first?
Well, the MMRTG is active today on the Mars Science Lab that's on Mars. So we started developing that one back around 2001 or so, and it's operational. We've got 2 more copies of that were built at the same time. One of those will go on the Mars 2020 mission that will launch in 2020. So that's the system that we have in hand. It's ready to go. We can build more copies of that, and DOE builds those for us. We are making technology investments in potential enhancements.
I understand you're stalling the ASRG, right?
The SRG, we're just looking at the technology, the
Okay.
basic conversion technology itself right
How
now.
about the kilopower?
Kilopower is an investigation that other parts of the agency are looking at for potential fission systems. And
Purely investigational at this point.
it's still technology development.
So I'm going to try to squeeze one more question in here, if I may, Mr. Chairman. So is there any chance that we could make this plutonium power available to commercial partners, the commercial sector, and is that legal going forward? Other missions?
We
we
haven't spent any time working on that.
Yeah, I don't have information.
So that's a novel idea to you?
We certainly haven't had any asks for it.
Okay. Thank you very much, Mr. Chairman. I yield back.
Yes, sir. I now recognize the gentleman from California, Mr. Rohrbacher.
Thank you very much, Mr. Chairman, and we get a great education here. You know, this is, I feel like I'm talking to the greatest experts in the world, and for us to hire people like this individually would be just impossible. So thank you very much for your testimony. And with that said, I sort of look at myself as a student who hasn't done his lessons yet on this particular issue. So let me ask this. The solar solar power is one way of promoting and actually providing the energy that we need, at least for closer in space exploration missions. But solar power will not work further out in space. Is that correct?
The farther away you get from the sun, the less power you can get off the same solar panels. So if you go to Jupiter, it's only 4% of what you can get from Earth with the same solar panels.
Okay, so we are going to, with anything that goes beyond Mars, this will not affect any calculations as far as for a Mars mission. Is that correct?
Mostly correct. There are uses where the environment is, if you look at the rovers on Mars, they're not always in the sunlight because of the way the sun changes as Mars goes through its seasons. So on MSL and Mars 2020, actually having the RTG makes it operational year-round as opposed to having to stop during the winter.
How about on the far side of the moon?
Far side of the moon, one of the problems you have in the moon is you get 2 weeks of darkness no matter what part of the moon you're going to be on. And these can enable missions, possibly rovers or landers, to survive that lunar night as well.
Okay, so this does have some application other than just deep space.
That's correct. It's not just distance. It's also any place that may be dark or dusty and not have enough sunlight.
Okay, and I understand Japan has a large, how do you say, storage, not storage, but they possess a large amount of plutonium left over from their reactors?
I'm not familiar with that at all.
Okay, is anyone familiar with that and the possibility that that could be used to produce the plutonium-238 that we need?
Congressman, I'm not aware of any inventory.
All right. Now, what about Russia? Is Russia, I understand they actually produced this at one point. Is that right?
Yes, that's correct. And previously, the United States purchased material from Russia, and that's what we have in our current inventory. But there's no plans at this point to purchase additional material.
So is it possible that we could, if we can get our relations back together again, as they were a few years ago, might have, this could be some area of cooperation between Russia and the United States in providing this material and perhaps joint deep space projects?
Yes.
So I was actually the co-chair of the 2009 report, and we looked at the situation with Russia at the time. And apparently, from what we could tell, they pretty much had sold or were planning to sell to the United States everything that they had left. There were discussions that they brought up suggesting that if we wanted to fund a plant in Russia, that they would be interested in taking our money and producing plutonium for us. It was not going to be cheap. And at least at the time, talking with the people that were at DOE, they did not think that that would be an appropriate thing to do, nor were really the funds there in place to do that. So there are, of course, the Chang'e 3 lander that the Chinese landed on the moon not too many years ago did have radioisotope power supplies on board. They're very small. From what one can tell from the open literature, those probably did come from the Russians. Perhaps some leftovers of what they had. But as far as there's anything out there that is available in the open literature, the majority of this material that's left in the world is in the United States, and it's that 35 kilograms.
And it has to be produced. This is something, you have leftover plutonium from nuclear power plants, but that plutonium needs to be worked on and produced through another process.
So that's actually a different kind of plutonium. That's the same thing that one uses in weapons. It's plutonium-239.
Right.
The power supply is 238. That one difference makes all the difference in the world. It turns out that the plutonium-238 gives off power by actually decaying. Half of it goes away after about 87 years, and that's the reason that the Voyagers will be going offline sometime in the mid-2020s, because they're nuclear batteries effectively are winding down. So you do indeed have to make it. You make it out of neptunium-237.
And that comes from where?
The neptunium-237 was left over from the United States weapons program. There's about 300 kilograms of the material that's left in under storage at Idaho National Laboratories in Idaho, and the United States no longer has the capability of making
Okay,
that.
but none of that comes directly from leftover material from nuclear power plants.
Not in the United States, sir, no.
But but perhaps in Russia.
There are some processes that one can use, but again, one has to do a lot of processing of material, and of course, we haven't been reprocessing material for the commercial world in the United States since the Ford administration. It's been a security issue.
No, I understand that, but we're looking just reprocessing for this specific 238, and not that will come from plutonium that is not in any way related to what's left over from a nuclear power plant. Is that correct?
Right.
Okay. This is not reprocessed plutonium
Right.
from a nuclear power plant.
No, it is not.
And where does that plutonium come from that this is that the 238 comes from?
So
Once it's
again,
processed.
So again, the plutonium-238 is material that we actually made out of the neptunium, and that we've had as heritage material that's been left over from other programs in the United States. Again, once you make it, it's half of it goes away in about 87 years, and so that's one of the reasons that part of that 35 kilogram inventory is not currently up to specs because it's old enough that it has decayed away. And so that's the reason for needing to upblend it with new material in order for it to be used in future missions.
And for long-term, any long-term strategy that would have us in deep space, this is an issue that we must deal with, because someday we're just going to reach a brick wall and we can't go any further. I hope by then perhaps we will have not just Russia but other international partners that could work with us on this, so the total cost isn't the American taxpayer, but who knows? We'll see. But in the meantime, I'm pleased that you are alerting us to this long-term need that it should be there on one of our considerations as we're looking through our budget. So thank you very much for your testimony today.
Thank you, Mr. Rohrbacher. There was just a couple other issues that I wanted to address. Dr. McNutt, NASA indicates that a production rate of 1.5 kilograms per year is sufficient to meet its needs, and that is based on the use of MMR-TGs. The 2009 National Academy of Science report that you chaired included an attachment, which was a letter from NASA to DOE expressing PU-238 production needs, and it states, the Mars Science Lab and the Outer Planet Flagship 1 are designed to use the multi-mission radioisotope thermoelectric generator technology. The rest of the missions assume the use of advanced Stirling radioisotope generator technology, significantly reducing the quantity of PU-238 required to meet the power requirement. Is there a more recent letter from NASA to DOE that might clear some of the seemingly incongruencies, or whatever you'd want to call it here?
Right. So to the best of my knowledge, there's only been one letter that at least has made public since then, and that was issued in 2010. I was on the Planetary Decadal Survey that came out in 2011. We had access to that. That was the letter that had reduced the need to the 1.5 kilogram per year level. The reason for that reduction from the 5 kilogram per year level that had been issued in the previous letter in 2008 by Administrator Griffin was because that included elements of the Constellation program that required pressurized rovers for human excursions on the surface of the moon. Once the Constellation was canceled, that need went away, and that was reflected in the letter of 2010. To the best of my knowledge, there has been no series of letters that have been interchanged between NASA and the Department of Energy since then, and one of the items that we flagged in the 2009 report is that having a publicly available assessment of need on a yearly basis or so is actually something that perhaps should be reinstated.
Well, one other thing, now that SLS and Orion are back online, so to speak, is it a possibility that we might need more than 1.5?
Yes, there could be. So one of the exercises that we went through in the 2014-2015 timeframe was putting together what's called the Nuclear Power Assessment Study. We had a variety of people from all of the DOE labs, from a lot of the NASA centers as well, trying to look forward at what sort of needs there might be, look forward at what sort of a role fission might play, and also look forward at what sort of needs that there might be for the human exploration missions. We had representatives from HEOMD from NASA on the panel that did the work. Their words to us as we were putting that report together was that there were no current requirements within human mission exploration for NASA, and that there really wasn't any way of coming up with a number because those requirements did not exist, and something that would be studied in the future. And so that's one of the reasons why that all of this discussion is really hinged on the 1.5 kilograms per year. And as Mr. Schurr said, a lot of this is also reflected in the actual cost of the individual missions, and it's sort of a delicate balance of how much money you have for the missions that would need the material, and then you don't want to overproduce this stuff because it does start decaying away once you've produced it.
Right, okay, thank you very much.
Certainly.
And then I'm taking a chair's privilege here. I want to ask another question of Ms. Bishop. How will projected production rates be affected when the Advanced Test Reactor at the Idaho National Laboratory undergoes the year-long scheduled maintenance shutdown beginning in 2020? And has the ATR been qualified for supply project work?
Thank you for the question.
Okay.
Currently, our activities supporting the Advanced Test Reactor, we are doing a lot of planning activities right now to ensure that we are ready to produce PU-238 in the reactor when we finish the core internal changeout activities in 2020. Currently, we have completed a trade study with the Advanced Test Reactor to identify optimum positions within the reactor and develop that initial plan for how we would go about producing the material. With some additional funding that was provided in fiscal year 2017, we are accelerating an experimental campaign to verify those calculations regarding our projected output of material.
Okay.
And with that, we're also focused on developing and finalizing a standard target design that we would utilize for both the Advanced Test Reactor and the High Flux Isotope Reactor by 2019, with the goal when ATR is completed its core internal changeout, we would be ready in 2021 to insert targets and start producing plutonium-238.
Great, okay, thank you very much. Then I have a request of you, Mr. Schurr. Dr. McNutt's testimony states, an assessment was made of the true cost impacts, and a final report was transmitted from NASA to the Office of Management and Budget in the fall of 2013. Would you please provide a copy of that report, of the report that Dr. McNutt referenced in his testimony from NASA?
You were on the panel with me. It was the zero-based review study.
We'll take that action.
Okay, great. Well, this concludes our subcommittee hearing this morning. I want to thank every one of you witnesses and all the members, although I'm the only one left standing up here, and those of you who came to listen. We really appreciate it, very interesting, and I would like to adjourn the meeting.